Welcome to lecture 32. So we'll get started with a recap of what we were doing in the last class. So you can recall that we had started talking about material symmetry. Okay. And in this context, we thought of the deformation from two reference configurations. Okay. So these are two arbitrary reference configurations, which can, of course, be related through a deformation gradient big H. Okay, so we call the left one first reference configuration denoted by gyref1, and the second one as the second reference configuration, okay, gyref2. And then we have our deformed body sitting here, and from each of the reference configurations you can find a map to get to the current deformed body. So from 1 it is through F1, and from 2 it is through F2. Okay, and what we said is that the true stress in the deformed body, so in the deformed body at any point P, the stress should be independent of the what reference configuration we choose, because we are free to choose any reference configuration. That doesn't mean that the stress in the current configuration will vary, right? Otherwise it becomes arbitrary then. So that helped us to write that the response of the, or let us say the Cauchy stress response function with respect to reference configuration 1, we denote by sigma 1 hat, and the Cauchy stress response function with respect to reference configuration 2, we denote by sigma 2 hat. So if we do sigma 1 hat F1, then it should be equal to sigma 2 hat F2. Okay. Furthermore, from this map, we can see that F1 is actually equal to F2 times H. All right. So if we substitute this over here, then we have sigma 1 hat F2H is equal to sigma 2 hat F2. And F2 is just a nomenclature. We can very well replace this by F. Okay. So this is going to hold. So we'll say that it holds for all F such that det F is greater than 0, right? Because F is corresponding to a continuum mechanics deformation. But for H, the only restriction was that its determinant is not equal to 0. Because H did not correspond to any continuum mechanics deformation. It's just two reference configurations which you chose arbitrarily, and they need not be realized through any continuum mechanics deformation. So all that we want is that H is not equal to 0. Okay. Further, you see, it is possible. So this is what we were discussing in the end. It is possible that the two configurations are such that, see, not always, but it is possible that by luck, the two configurations are such that the response function, so I'll just say here, it may be possible for a H such that sigma 1 hat is equal to sigma 2 hat. Okay, and let me denote that by just sigma hat. It is possible that the response function is the same. Now, can you guys think of when is that possible that the response function is the same, even though the reference configurations are different, and you see that it should actually follow this formula the reference configurations are different, so likewise the response functions would be different. But is it possible, let us say by luck or by some physical argument, to say that there could be two configurations for which the response functions are actually same? Can anyone tell me when is that possible? Fh is equal to f. Well, no. See, we are talking about the response function, not about the argument. The arguments can be different, but we are right now talking about the response function. So this will mean that if the response function is same, then sigma 1 hat of f would be same as sigma 2 hat of f for all f. So is it possible that you apply the same deformation gradient big F in both the cases and you still get the same stress finally? Can you think of a physical case when it would be the case that the response function is indeed the same? So Manoj says if it is just rigid body motion case. So you mean for big H rigid body motion or for big F body subjected to hydrostatic pressure? Well, none of the answers are correct actually. So you have to think of, I had given a hint in the last class. What does response function depend on? So all the information of kinematics or the deformation is in the argument of the function, that is big F. But what will be the formula of the response function? It depends on the microstructure of the material, which leads the response to be isotropic or orthotropic or transversely isotropic, and likewise. So Nikhil says if the two configurations coincide with each other. So what's the meaning of that? They just geometrically coincide? You mean they occupy the same space? And Toiba says it is symmetric. Again, what's the meaning of that? Suppose that you have a material which has fibers in it. It has family of fibers. Let us say it has two sets of family of fibers. Okay, and think of your big edge so that you are simply rotating it by, let us say, 90 degree. So it has two sets of family of fibers which are perpendicular to each other. Okay, these are perpendicular. So if you rotate this by 90 degree, so these fibers are, it's like in a continuous fashion. It's not discrete because there are so many fibers in the bodies, but I can't draw all of them, no? So you can think that it's uniformly distributed parallel set of fibers, but directions you can see what it is. And sorry, again, it's 90 degree. I should have been more careful. Let me actually do that. So H is rotation by 90 degree. Now, what do you think? So suppose you are at a point P here, and that point goes, let us say, over here. So locally at this point P, the orientation of the fiber is similar. Can you see that? It's similar. So when this point gets subjected to the same deformation gradient big F, then what should be the stress, the Cauchy stress outcome? What do you think? So it's a family of fibers, two parallel family of fibers at perpendicular angle to each other. You rotate by 90 degree, the orientation of the fiber does not change. And then you apply the same deformation to both the same big F and measure what is the Cauchy stress developed at point P in the deformed configuration. Don't you think then in that case the Cauchy stress will actually be the same? The sigma will actually be the same because you see locally the body is looking same. Locally the body has same microstructure, same neighborhood, and if you have an energy function or if you have a response function which just depends on the local value of deformation gradient, not on what is the deformation gradient in the entire body. If that is our model, then don't you think that since the material is locally the same, therefore whatever deformation you apply to the two bodies, I mean, if you apply the same deformation to the two bodies locally, which means you're applying the same big F, then the outcome should be the same, isn't it? So I can say that because the microstructure is the same locally, final response of the body in terms of Cauchy stress should be same. Let me make this more clear. So suppose you have, a body which is actually in the form of a circle, okay? And it has just one family of fibers. You rotate this by 90 degree. Then the disc-like body will occupy the same region, okay? It will occupy the same region, but the fibers in it gets oriented differently, okay? Now suppose I do the deformation which is corresponding to uniaxial loading, okay? In both the cases, let me apply the same kind of, the force P, uniaxial loading. And since maybe it is even easier if you think of uniaxial stretching because we are thinking of applying deformation here. So suppose I do uniaxial stretching horizontally. In both the cases, it's the same uniaxial stretching but horizontally. And here also. Now, what do you think? Will you get the same stress? Will you get the same outcome? You do the same stretching in both the cases. In the left hand side, the fibers are perpendicular, and in the right hand side, the fibers are aligned with the direction of the stretching. Will you get the same response? So if you at a point, let us say P, you measure the what is the outcome, the Cauchy stress, will you have the same? It won't be the same, right? Because locally, I mean, this is something you all know. For example, if the fiber were strong, then it is difficult to pull the material along in the direction of the fiber. But if you somehow manage to pull by the same amount, then the stress developed will be higher in case the fiber is aligned along the direction of the fiber. Sorry, in case the loading is aligned in the direction of the fiber, right? And so why? So I mean, that's the physics, but finally you can say that the response is different because the local microstructure is not the same. The orientation of the microstructure is not the same in the two cases. But the same thing, if if you have two family of fibers perpendicular to each other and rotate by again 90-degree, then you can see that the microstructure environment will again be the same, and therefore the response should be the same, isn't it? So this is what I was trying to say here, that in for a general reference configuration having arbitrary body shape, if locally the microstructure of the body is same after application of big H, then the response function should be the same. So Vishwas was asking the properties along both the fiber directions need to be same. So yes, you are right. The property along the two family of fibers must be the same. Otherwise, again, you will get different answer. So this is, we just gave a specific example to illustrate that it is possible that even if you have two reference configurations, related by big H, it is possible that the response function, the Cauchy stress response function, will be the same. But it's not always. It is not going to be for all H. Okay. So, this brings us to the final definition for the material symmetry that we wanted to discuss. So think of set of all such H. Think of set of H. So H such that determinant of H is not equal to 0, and also the sigma hat F is equal to sigma hat FH, because the response is same and the two deformation gradients, from one if it is F, then from the other it will be FH, right? So if this holds for all deformations, that means for all big F, and I should say for all non-singular, no, because that F has to be not equal to 0. Well, for all F such that that F greater than 0, because it's a continuum mechanics deformation. So either you write like this, or you say that there's an H such that that H not equal to 0, but the response function sigma 1 hat is same as sigma 2 hat. You can write in either of the two way. So for all such h for which the response function becomes the same, or the first statement that sigma hat f, because you see how did you get the first statement, that is from here. Since the response function is same, sigma 1 hat and sigma 2 hat are same and equal to sigma. Okay. So this set of H is what we say is that it comes in the symmetry group of the material. Okay, we can also say, I mean, for now that this is the set of transformation of reference configuration which leaves the stress response function unchanged. Now I'll do one more constraint here. I'll further constrain this H to be, let us further constrain the H. Such that det H is not equal to 0. So det H is equal to 1. Let us further constrain the H such that det H is equal to 1. What is this actually doing is that, you remember the relationship for the density? It was rho naught equal to rho times det F. Now, if you think of what is the density in the two reference configurations, if det H is equal to 1, this will ensure that densities in the two reference configurations are same. Isn't it? Rho naught will be same as equal to rho. So densities in the two reference configurations will be same. So we say such reference configurations for whom the which are related through this big H such that det H is equal to 1. Furthermore, the response functions are same. So we say such reference configurations as mechanically equivalent reference configurations. As mechanically equivalent. Okay, see, it's really interesting. It's like, suppose somebody was doing a test on a material or on a specimen. Okay, yeah. So somebody was doing a test on a material. He had the body or sample. He did a test and he wanted to repeat the test again, but he went out for a coffee. In between, a technician comes and transforms the body through this H. And if that person who was doing the test comes back to do the repeating test, he will find his test to give the same result again, isn't it? Because he has still the same mechanically equivalent configurations. Although it's not the exact same configuration, but mechanically it is the equivalent configuration. Okay. So finally, mechanically equivalent configurations, we can think of a group, denoted by G, is equal to all H such that H is equal to plus minus 1. Okay, I think I just said 1, no, it should be plus minus 1. equal to plus minus 1, because in that case the density will be rho naught equal to rho into mod of det f. So still the density will be same. Okay, so we are also allowing minus 1 because like I said that h is not corresponding to any continuum mechanics deformation. So think of all h such that that h is equal to plus minus 1 and sigma hat of f is equal to sigma hat of fh for all f such that that f is greater than 0. So this group, this forms a group, and this is called symmetry group of the material. Okay, and I should say more specifically it is called material symmetry group, okay, of the material, and with respect to configuration chi 1. See, it is important to qualify with respect to which configuration we are talking about the material symmetry group, because it is very likely that the symmetry group can change if you take different reference configurations. Just like, think of a reference configuration in which the fibers are very nicely parallelly aligned, and another reference configuration which is a distorted body and the fibers have gotten somehow like this. Then you can see that the two bodies will not have the same symmetry group. Okay, so symmetry group is, it's not like if you have the same material, let us say aluminium, then symmetry group is always fixed. Symmetry group is not just depending on the material but also on the reference configuration, with respect to what reference configuration you are trying to talk about the symmetry group. The material symmetry group. So this is of course applicable for isotropic material. Can you think of what will be the symmetry group for such material, for isotropic material? What will be those sets of H for isotropic material which leaves the stress response function unchanged? Anyone, can you guys tell me? So look at this definition and tell me what do you think? What will be those set of H which will be in the material symmetry group of isotropic material? I mean, you think of what has your notion been about isotropic material? I mean, you think that it has same property in all directions, right? What does that imply for big H? So Manu says identity matrix for big H. So identity will be for every material, whether it is isotropic, transversely isotropic, or whatever. Identity lies in the symmetry group of all materials. Well, identity leaves the reference configuration unchanged, no? You get back the same reference configuration, then obviously sigma will be the same. So see, for isotropic material, let us say this is the isotropic body. So we say that it has same property in all directions, same property. So even if you rotate the body and then apply the same deformation, then you should get back the same response, right? Or stated differently, you apply stretching in this direction or you apply stretching in this direction, response is same, right? Because it's an isotropic material. So this is like even if you rotate the body by any amount, the response function will remain unchanged. Don't you think so? If we rotate the body by any amount, because locally the microstructure of the material is still like isotropic. Rotation does not do anything, no? If we rotate the body by any amount, the response function does not change. Okay, so this means for all, so H is actually set of all rotation tensor. And also you notice that for rotation tensor, determinant of rotation tensor is 1. So it is satisfying that criteria. That H should be equal to plus minus 1. But also you notice what we wrote there was that the response function is that such that sigma hat of F has to be equal to sigma hat of FQ. Okay, but you know that from objectivity, if you just think of objectivity, what should the function sigma hat be? So sigma hat for QF, that is equal to Q times sigma hat of F into Q transpose. So this is the outcome of objectivity, the restriction on this stress function. We want to further see what will be extra restriction due to this symmetry, which says that the response function should also obey this property. So objectivity says this is the case for all Q rotations. Whereas material symmetry, MS, it says the sigma hat as a function of F is actually equal to sigma hat of FQ. For all Q in that symmetry group G. So in the for objectivity, it is all rotations all the time. It is independent of symmetry. Whereas in material symmetry, the Q that comes, it is only for those Q which are in the symmetry group. So do you indeed see that it is an extra restriction on the response function? So response function cannot be arbitrary. One, that it has to satisfy objectivity, but that is not enough. It has to also satisfy material symmetry property. And to illustrate it further, one can also denote the symmetry group in terms of energy function. Denote the material symmetry group in terms of energy response function. If the body is thermoelastic, So that means psi hat as a function of big F. So what, in terms of this, it says that the symmetry group G is such that it is for all H such that det H equal to plus minus 1, and furthermore psi hat of F is equal to psi hat of Fh for all F such that det F is greater than 0. So notice earlier we wrote it in terms of sigma, right? The symmetry group, we wrote it in terms of sigma, but we can also write that in terms of psi hat. But of course, it's possible only if you have a thermoelastic material. And I guess the idea should be, you should be able to see this. Why psi hat is remaining unchanged? Because if it has to lead to same response, shouldn't the corresponding energy also must be the same? Isn't it? And in fact, you can also derive, if psi hat of F is equal to psi hat of Fh, then you can show that the corresponding response function will be such that sigma hat of F will be equal to sigma hat of Fh. It is possible to derive this. So, which means that the two definitions of the material symmetry group are same. Whether you write in terms of Cauchy stress or you write in terms of Helmholtz free energy psi hat, the two definitions are same. And this thing showing that if one holds, the other one will also hold. Maybe you should try to do it. I can ask you in the major exam, a probable question. Okay, for thermoelastic material, you know what is how are the two response functions related? Sigma hat and psi hat, how are they related? You already know this, isn't it? So for example, sigma hat, can someone tell me what is how is sigma hat related to psi hat using entropy inequality? Rho times del psi hat by del F, was it this? Or rho naught times del psi by del F, perhaps. First P order. Okay, yes, this is for P. Thank you. But what about sigma? What do you get for sigma? Sigma is 1 over J P F transpose, which means this becomes rho into del psi hat by del F into F transpose. Okay, yes. So starting from psi hat of F is equal to psi hat of Fh. Let me try to show you that indeed you can derive this. So then it won't come in the major exam. I think it's good to show you. So think of this Fh as some Z, some Z. So if I find out del psi hat by del Fij, then that's equal to del psi hat by del Z KL into del Z KL over del Fij, isn't it? So I'm just differentiating this with respect to Fij, this identity. So on the left hand side, we then have, we know that it is and let me also multiply by rho naught on both the sides. Okay, so or if we even don't do it, it is fine. So it is del psi hat by del f ij. So del psi hat by del f ij is equal to del psi hat by del z kl. And what will be del z kl by del f ij? So zkl is fkm into hml. So del zkl by del fij is then delta ki into delta lj into hml. Okay, so we can write that here, delta ki into delta lj into hml, which is same as del psi hat over del z ij into hml. I guess I'm making some mistake. Zkl by del fij. Okay, this is mj. Sorry, this is mj. So this then becomes IL into HJL. Okay, so from here, what do we get? So del psi hat by del Fij is then, and you see rho naught, let me now multiply by rho naught on both the sides. So we also get rho naught times del psi hat by del Fij is equal to same rho naught times del psi hat by del ZIL evaluated at ZIL into HJL. But then del psi hat by del F is like the Piola-Kirchhoff response function, no? So this whole thing you can write as P hat ij evaluated at Fij. And on the right hand side is then the Piola function P hat il evaluated at Zil. But you see it's the same function because derivative of psi hat has to give you Piola-Kirchhoff stress tensor times HJL. And if you go back to tensor notation, it then gives you P hat is then, so P hat at F is equal to P hat at FH into H transpose, isn't it? Okay, so having derived this, let us try to find out how will sigma be then related. So sigma hat of F, we know that this is 1 over J, and J is det F, right? So I'll write that also, 1 over det F into P hat of F into F transpose. Is that correct? And likewise, sigma hat at fh, what is that going to be then? So that's 1 over determinant of fh into p hat at fh into fh whole transpose. Okay, and finally, since h is such that det h is equal to, I mean, if you choose if h is equal to q, let us say rotation, then isn't det fh is equal to det f into det h, but det h is then 1. So we can write here det f into det h, which is actually 1. And then here we have p hat fh into, okay, am I making some mistake somewhere? Okay, we'll see. This is then H transpose into F transpose. And this finally is 1 over det F into, and P hat FH, we just saw it is P hat. Okay, look here. So what is this? This means P hat FH, or maybe P hat FH into H transpose is P hat F itself, no? So from here, if we come back, we can notice that this thing inside the bracket is just PF. So this is just PF into F transpose. Okay. So what you see is that right hand side is again is the sigma hat function, no? Sigma hat is F at F. Okay. So finally, we are getting that sigma hat FH is indeed equal to sigma hat of H. What we wanted to prove, no, that if psi hat of fh is equal to psi hat of fh, then it automatically implies sigma hat of f is equal to sigma hat of fh. So the two definitions of material symmetry that we did earlier are actually the same. Okay, where h simply has to be such that determinant of h is equal to plus minus 1. So if that is the case, then the two definitions of symmetry group are same. Okay, now let's think of in terms of psi hat. In terms of psi hat, objectivity implies psi hat of f is equal to psi hat of qf, right? Which allowed me to say that psi hat is just a function of c. Now if I come to symmetry, suppose it is isotropy symmetry group. For isotropy, then this means psi hat of f is equal to psi hat of fq, isn't it? For all q rotations, for all rotations, which implies what happens to c, you see, because psi hat has to be a function of c from objectivity. So how is c transforming? If f changes to fq, how does c transform? So you can show that it is then going to change to q transpose cq. But also notice that this is same as psi hat of minus q transpose into c into minus q, because two minuses cancel and become 1. So that means if it holds for q, then it is also going to hold for q minus, sorry, for minus q. Because the function has to be always objective, and symmetry told me it has to hold for all proper rotation. But then we see that due to objectivity, if it holds for proper rotation, then it also holds for improper rotation. So therefore, in symmetry group, we actually apply all the rotation, all orthogonal tensors, plus as well as minus, minus corresponding to reflections. Okay, so I'll write that isotropy symmetry group is for all q which are orthogonal tensors such that whose definition is that QQ transpose is identity, and also that Q is equal to plus minus 1. Okay, this is for isotropy symmetry group. So I'm going to stop here and we'll continue tomorrow. In the meantime, if you have any question, please feel free to ask me.
Sir, for isotropic material, we tell infinite plane of symmetry kind of thing. So, but we are putting restriction on the group. So whether it can contain all such combinations, because we apply load in any direction, we are going to get the same response.
Yes, so also, yeah, it contains all. Because Q is any Q, no? So, and there are infinite such Qs. Q, if it is any Q, then it's infinite of them.
Okay.
Yes. How can you characterize Q? Q can be characterized by the axis of rotation and the angle of rotation. Now, axis of rotation is infinite because it can be any direction. Furthermore, angle of rotation can also be infinite. So it's infinite into infinite.
Okay. Got it.